All right, we're moving along. We're on chapter 8 already. Chapter 8 is all about oxidation and reduction chemistry. We already covered this a little bit in lab, but let's talk a bit about the history behind it. Historically, the definition was a bit wrong. They said that oxidation is where something reacts with or gains oxygen. Makes sense, right, based on the name? Reduction, on the other hand, is where you remove an oxygen from an oxide. So, for example, if you've got iron oxide and you remove oxygen from it, you get elemental iron back out. That would be a reduction reaction. We know today that the chemistry behind redox is a lot more complicated than just oxygen. Who remembers what redox is really about, based on our pre-lab lecture? What do you think? Yeah, moving electrons, right? So in lab we said it's not just oxygen that's being taken or added. It has to do with the addition or removal of electrons. And anytime you see these reactions, they're always coupled in a pair, right? So there's always one side that's an oxidation and then another side that's a reduction. So the modern definition is a lot better. The modern definition says oxidation is what? Is it gain or loss of electrons? I taught you guys oil rig, right? Oxidation is loss. So is loss of electrons, where reduction is gain. This covers a lot more redox chemistry. So the way I remember it, like I said in lab, is oil rig, oxidation is loss, reduction is gain. There's also some other ones you might see. Another common one you'll see in chemistry classes is Leo goes grr, so Leo the lion. So losing electrons is oxidation, gaining electrons is reduction. So whichever one you prefer. I like oil rig, it's nice and simple. But find mnemonics that help you understand some of these key things. All right, there are some other things that you might notice with a lot of these reactions, so let's make a list of both oxidation and reduction. We said oxidation always has a loss of electrons. Reduction always has a gain of electrons. Oxidation often has a gain of oxygen, but not always. And we said reduction often has a loss of an oxygen. So if you get kind of lazy and you don't want to count electrons, but you see one molecule is gaining or losing oxygen, you can pretty quickly tell if it's an oxidation or a reduction. You can also look at the hydrogens too. There's often a loss of hydrogen in an oxidation reaction, and then a gain, let me put often, a gain of hydrogen. But the key thing to remember is that these first two are the best way of identifying a redox reaction. The other two, they're often but not always. So these are the best way to identify redox. Does that make sense? Pretty straightforward. All right, now we get to go into the nitty-gritty part of this, counting electrons. So let's talk about some basic electron bookkeeping rules. These are pretty straightforward, but I'll give you a handful of hints. The first one is that elements by themselves have no charge. So for example, if I just give you a sodium atom and I don't indicate that it's a positive charge, let's just assume that it's neutral and that it has no charge, right? So that's a really simple thing. The next one is you can make a really simple scale, and I'll show you guys what I like to do. Is let's make a scale like this. I'll have an arrow going up. This is more positive. This is more negative. Whoa, shoot. Sorry about that. And then in the middle we'll have our neutral atoms, meaning they're uncharged. Oxidation occurs when you're going from something that's more negative to more positive or neutral to more positive. So oxidation is moving in that upward direction, where reduction is really moving in this downward direction. So if you're going from something that's neutral to more negative, you're obviously gaining electrons, and that's going to be a reduction. Or if you're going from something that's positive to negative, you're also gaining electrons, and that's a reduction. Does that make sense? So it really depends if you're gaining or losing electrons, and you can tell by whether or not you're going from positive to neutral or neutral to negative or so on. All right. So those are the two key things you have to keep track of when you're doing these. So let's do some example problems. And I like to start with a really simple one. Let's do iron and oxygen. Shoot. My adapter's going out on me. All right, so if you've ever left something made of steel outside, steel has iron in it, and it will react with the oxygen in the air, that's O2, to make rust. What's the molecular formula for rust? What do you guys think for iron oxide? Or do we know? What do you guys think? Do we know the charge for iron? No, it's a transition metal, so it's a little trickier to know the charge. However, I'll give you guys a hint. This is normally going to form iron 3 under atmospheric conditions, so iron likes to be iron 3. So we would react this to form an iron 3 cation, and then we'd have oxygen, which has what charge? -2, so 2 minus. All right, so knowing this, what would our charge be for iron 3 oxide? Yeah, Fe2O3, exactly. So it'd be Fe2O3. That's good. It's like we got it right. All right, is this bounced yet? No. All right, so first thing we need to do with any of these reactions is bounce them. All right, let's start with the heaviest atom. We've got iron. We've got 2 on the right, but only 1 on the left, so I'll put in a 2. All right, and then the oxygen. We've got 2 on the left, 3 on the right. What do you think we should do? Okay, 3 in front of the oxygen. So now we've got 6 on the left, but only 3 on the right, so I'm going to have to put a 2 here, right? And then what do I need to do? Yeah, change the 2 to the 4 on iron. So not too bad. We've got it balanced now. Now what we need to do is kind of take a look at each of these elements in here. So iron, over here, what's its charge? Not everybody all at once. Is it? When it's by itself? It's neutral, right? Okay. So it's neutral because it's by itself. What about over here? What was the charge again? We said it was going to be 3 plus, right? So Fe3 plus. All right, now the question is, did we gain or did we lose electrons? Looks like we lost 3 electrons, right? So let's make a note. Each Fe lost 3 electrons. We know that because we're going from neutral to positive, right? So is this going to be an oxidation or reduction for iron? Oxidation. So Fe is oxidized. All right. Like I said before, though, you never have a reaction that's just an oxidation. There's always a reduction reaction that accompanies it. So now let's focus on oxygen now. What's the charge for oxygen in O2? Neutral. It's by itself. All right, and then over here, what was the charge for oxygen? 2 minus, so we'd say O2 minus. Okay, so if we're keeping track of electrons here, it looks like we gained 2 electrons for each oxygen. So each O gained 2 electrons. So this must be a reduction, right? So oxygen was reduced. The other important thing to keep track of is the total number of electrons that are moved, right? So we had 4 irons. They each lost 3 electrons, so that's a net movement of 12 electrons for the iron, right? If we check the oxygens, we've got 6 total oxygen atoms on the left-hand side. Each of them gained 2, so that's 12. You need to make sure that your electrons match on the reducing side and oxidizing side. It's not something we're going to get into a lot, but if you continue on in chemistry, you will have to bounce electrons if they're not already bounced. Let's do another one. Let's do CuO. What's this going to be called? Copper oxide, or do we have to have a Roman numeral in there? Is it going to be copper 1 or copper 2? Copper 2 oxide. Okay, so copper 2 oxide plus zinc will react to form zinc oxide plus copper metal. All right, first thing you should do is determine whether or not your equation's bounced. And then what I want you to do is identify whether or not an element was reduced or oxidized. So I'll give you guys a minute to work on this, but check with your neighbor and see if you agree with them. There's also an option for neither oxidized nor reduced. And give me a thumbs up if you think you identified it already. Okay, a couple thumbs. If you're stuck, I'll give you guys one hint. Let's take a look at the oxygen here. What's the charge on that oxygen? 2 minus. What's the charge on this oxygen? 2 minus. So is it getting oxidized or reduced? No. So really all we're looking at in this reaction is copper and zinc, not the oxygen. So I'm just going to add in some arrows here. All right, another check of thumbs. Who thinks they got this one? Sideways thumb if you're still working on it. Thumbs down if you're like, what is he talking about? Okay, that's fair enough. I saw a few thumbs down. So let's look at the first one, copper oxide. We said that the oxygen on copper oxide, this guy right here, must be 2 minus, which means the copper is going to be what? 2 plus. Okay, and then the copper on this side, on the right-hand side, is by itself, which means it's going to be what? Neutral. So did we gain or did we lose electrons going from left to right? Looks like we gained electrons, right? If we gain 1 electron, we'd eliminate one of the positive charges. If we gained a second one, we'd get rid of both positive charges. So copper gained 2 electrons. Is that a reduction or an oxidation? Reduction. So copper was reduced. All right, now let's do zinc. Zinc over here, what charge will it have? Neutral, it's by itself. And then on the right-hand side, what charge will zinc have? 2+. So it'd be zinc 2+. So in this case, zinc lost 2 electrons, right? It went from neutral to a positive charge, so it must have lost electrons, which means that zinc was oxidized in this case. And again, if we try to keep track of our electrons, we can see that copper gained 2 electrons, so that was a net movement of 2, where zinc lost 2 electrons. That means we've got a balanced number of electrons being gained and lost in this overall reaction. You guys want to try a couple more? Okay. I know these can be confusing. Let's do magnesium. That's the metal we work with that produce bubbles in lab. Chlorine, Cl2, is the war gas. And we'll make magnesium chloride, which will have what formula? Be MgCl. MgCl2, right? Magnesium's got a positive 2 charge, chlorine's -1, so it'd be MgCl2. Is this balanced? Yep. So it looks like we're ready to determine which element was oxidized and which one was reduced, and then count the number of electrons. So again, I'm just going to put some arrows going up and then down. Then we can keep track of them that way. This one's deceiving. Oftentimes people see Cl2 on both the left-hand side and the right-hand side, but what's the difference between the Cl2 on the left-hand side versus the Cl2 on the right-hand side? Charge, right? Cl2 on the left-hand side is covalent, which means each of the chlorines is neutral, where on the right-hand side, each of the chlorines has what charge? -1, right? So because it's ionic, we have to keep track of the charge, where covalent molecules, we don't keep track of the charge. Yeah, that's the thing, is people get so hung up on oxidation involving oxygen, it doesn't have to involve oxygen. All right, so let's try this. Magnesium over here on the left-hand side, what charge does it have? Oh, it's by itself, right? Should be neutral. If there's no charge listed in that top right-hand corner, just assume that it's neutral. Over here, it's involved in an ionic compound, so what charge will that magnesium have? 2+. So it'd be Mg2+ because it's in an ionic compound. All right, so was this a gain or a loss of electrons? Looks like we lost 2 electrons, right? So magnesium lost 2 electrons. Is that an oxidation or a reduction? Oxidation. So magnesium was oxidized. All right, now let's do chlorine. Cl2 over here. Is that going to be neutral or charged, or what did we say? Neutral. It's by itself. It's a part of a covalent compound, so we don't have to factor in charge. The chlorine on the right-hand side, though, what charge does that have again? -1, so Cl-. So in this case, each Cl gained how many electrons? Just 1, right? Gained 1 electron. That means that this was a what reaction? Reduction, right? And again, we need to keep track of the electrons that are being transferred in both directions. On the top one, we're moving 2 electrons. On the bottom one, we have 2 chlorines, each moving 1. So it looks like it bounces out, right? You guys want to try another one? A little bit more challenging this time? Let's do another one with magnesium plus nitrogen. Goes to Mg3 and 2. What would we name the molecule on the right? Mg3 and 2. Or do we say trimagnesium? It's ionic, so we don't need to use mono, di, tri, tetra. What would it be called then if we don't need to use prefixes? Magnesium nitride. We don't need a Roman numeral because magnesium is not a transition metal, so it'd just be plain old magnesium nitride. All right, so let's work through this. Before you do anything, though, make sure everything's balanced, and then keep track of what's being oxidized and reduced. Yep. So the magnesium chloride, each chlorine has a negative charge. So each chlorine is going to be -1, where the Cl2 on the left is covalently bound. It's not ionic, so it's not charged at all. So if you see elements that are just by themselves, then they're always going to be neutral. But if they're involved in an ionic compound, then you need to keep track of what charge they have. Before I'm going to do any oxidation chemistry, I'm going to bounce it. So first thing I do is I look at the heavy atoms, magnesium in this case. We've got 3 on the right, but only 1 on the left. So I'll just plug in a 3 over here. And then nitrogen, we've got 2 on the right, 2 on the left. So that looks balanced, right? I don't think we need to make any more changes. Okay, so now let's focus just on magnesium for the time being. The magnesium on the left-hand side has what charge? It's neutral, it's by itself. The magnesium on the right-hand side must have what charge if it's ionic? 2+, it's in that column 2A. So it's going to be magnesium 2+. So each magnesium lost or gained 2 electrons? Lost 2 electrons, which means this was an oxidation or a reduction? Oxidation. Okay, let's do the same thing for nitrogen. This nitrogen, what's its charge? Neutral. By itself, where the nitrogen over here must have what charge? -3. If you look at the periodic table, it's in group 5A. It wants to gain 3 electrons to be like in noble gas. Yep. I'm just using it for space to kind of separate my work out. You're welcome to show it however you want. I kind of like doing it this way just to follow my thought process. So we've got N3-. So each nitrogen gained 3 electrons, which means that this was a reduction or oxidation. It's got to be reduction, right? And again, if we're keeping track of our electrons, we had 3 magnesiums, each gaining 2 electrons, so that was a transfer of 6 electrons. For the nitrogens, we've got 2 of them, each gaining 3, so again, that's a movement of 6. Yep?
So what happens to the double balance equation? It still affects like how many electrons and
It doesn't change the fact that something's being oxidized or reduced, but then your electron bookkeeping, the number of electrons moving one way or the other, doesn't match up. So it's just as important for redox equations to balance an equation as any other equation. If you go on and take the Gen Chem series, you're going to do a lot more with these. Sometimes you have to add in electrons to balance it or add in protons. We're not going to do that in this class, though. We're going to try to keep it simple. All right, so let's move on to the next section. I'm going to close this real quick and reopen it. So the next section is really similar, but now we're going to talk about oxidizing and reducing agents. But before we do that, let's define oxidation and reduction again. Whoop. So anytime we lose electrons, it's an oxidation. Anytime we gain electrons, it's a reduction. Not too bad. Oxidizing agents are a little bit different. Whoop. An oxidizing agent is defined as a reactant that oxidizes something else. All right, now here's where it gets a little bit tricky. So if it's oxidizing something else, that means that the thing being oxidized is losing electrons. That means the oxidizing agent is actually taking electrons in this process. Does that make sense? So in order to help something become oxidized, it must take the electrons from that thing being oxidized. Because we just said anytime something's being oxidized, it must lose electrons. So let's put that in. It takes electrons from the element that is oxidized. Now the ultra confusing part. If your oxidizing agent is taking electrons, is it being oxidized or reduced? It's being reduced. That confuses the heck out of students, where they're like, why would an oxidizing agent be reduced? And it's not that it's getting oxidized, it's helping something else be oxidized. That means it needs to be the counterpart to the thing being oxidized. Therefore, it must be reduced in the process. It's weird to think about it that way, but that's how chemists like to define it. Let's do the same thing for reducing agents, and then we'll do some practice problems. So reducing agents are a reactant that reduce something else. That means that it must give electrons to the thing being reduced. And conversely, that means it must be oxidized in the reaction. Confused? The wording makes absolutely no sense until you start working with it for a while. But the key takeaway, right, is an oxidizing agent, because it's oxidizing something else, has to be the counterpart to the thing being oxidized, which means it must be reduced. And same thing with reducing agents. Because they're helping something else to be reduced, they must be the counterpart to that, which means they're getting oxidized. So it is a little bit weird. It's like the yin and yang of redox chemistry. So let's do a few examples. So we've got SNO, tin oxide, plus hydrogen gas, goes to tin plus water. first thing I want you to do is to balance it and then do the same procedure that we did last time. So in water, that's a good question. What do you guys think? So he was asking about the hydrogen in this one. So treat it as ionic. It's a little bit weird, but because oxygen's more electronegative, that hydrogen is kind of acting a little ionic. So anytime you've got an element bound to a really electronegative one, you can treat it as almost being ionic. That's a good question. So I'll give you guys a hint for this one. Hydrogen by itself is what? Neutral. Over here we said we've got H2O. Oxygen is a lot more electronegative than the hydrogen, which means that this hydrogen is electron poor, which means it behaves like a positively charged hydrogen for this problem. Okay, so let's plug that in. And I'm going to put this in quotes because we know it is covalent, but it's behaving like a +1 charge. Which means our oxygen, on the other hand, must be behaving like what? Yeah. Must be behaving like a 2- charge. Okay? And then over here, what charge does this oxygen have? I'd say it's still 2-, right? Because it's ionic for sure. So this one's absolutely O2-. So if we're looking at the oxygens in this reaction, are they being oxidized or reduced or neither? Neither. There's no change in electrons. So I'm just going to erase this for the time being. Oxygen's not gaining nor losing electrons. So let's focus on the remaining element, the SN, the tin. So this one on the right-hand side, what charge must it have? +2, right? Because it's with an oxygen that's 2-. So it'd be SN 2+. And then over here, the SN will be what? Neutral. All right. So now we're in good shape. Let's go through and fill out the rest of the pieces, though. Okay, so for hydrogen, it looks like it lost 1 electron. So each H lost 1 electron, which means it was oxidized or reduced? Oxidized. All right, and then down here, if we're looking at the tin gained 2 electrons. Which means the tin was reduced. All right. So keeping track of electrons, we had 1 tin that gained 2 electrons, so a net movement of 2 electrons in one direction. And then hydrogen, we had 2 of them. Each of them lost 1 electron, so 2 electrons were moved in the opposite direction. All right, now the tricky part. Let's identify the oxidizing agent and the reducing agent. What do you think the oxidizing agent was for this one? Ooh. So down here we said the tin on that one was reduced, which means it must be the oxidizing agent or reducing agent? Oxidizing agent, right? We have to flip those. So in this case, if we go ahead and plug it in, it must be tin oxide is the reducing agent. Which means our reducing agent must be what? Hydrogen gas, right? So H2, because the hydrogen was oxidized in that step, H2 must be the reducing agent, right? The other thing that kind of tricks people is that you look at the entire molecule. However, when we're looking at what was oxidized and reduced, those were individual elements, right? When we went back and looked at this chart, I said each hydrogen lost 1 electron. I didn't say H2. I said each hydrogen. That means that hydrogen was oxidized. So if we went down here, we'd say, all right, this would be hydrogen, and then this would be tin. So down here, when you're looking at what's oxidized and reduced, these are individual elements, not the entire molecule. It's a little bit weird to think of it that way. Does that make sense? Yep.
So what would happen if a molecule
Had what?
or had an oxidizing something, a molecule had an element being oxidized an element?
Yeah, there are some weird situations like that. We're not really going to get into those as much, though. So let's do a couple more practice problems, because I know these are super confusing. So let's do vanadium oxide. So V2O5 plus H2 goes to V2O3 and H2O. And like I said, the hydrogen, when it's in water, because it's so electron poor, is behaving as an anion, or sorry, a cation. You guys want a hint? All right, let's look at the oxygens. So V2O5, over here, what charge would that oxygen have? Each oxygen? -2, it's ionic, right? So this would be O2 negative. Okay, over here, what charges would those oxygens have? Still ionic, right? So it'd still be O2 negative. Okay, and then we said over here, treat H2O as being ionic because oxygen's so electronegative, it's going to behave as O2 negative, right? Does that mean oxygen's being oxidized, reduced, or neither? Neither. So let's focus on vanadium and hydrogen, just like we did before. So I'll get some arrows plugged in. Yeah, let's bounce it too. What do you guys think I should do to bounce this? 2 in front of the hydrogens? Okay, so we've got now 2 hydrogens on the right, but only 4 on the left, so we probably want to put a 2 over here, right? Okay, so now we've got 4 hydrogens on the left, 4 hydrogens on the right. If we count oxygens, we've got 5 on the left and 5 on the right, so now it looks balanced. That's good. Okay, so now let's focus on vanadium with V. Over here, what charge must it have? This one's a bit trickier. So let's focus on the oxygens. We said we've got 5 of them. Each oxygen, we said, is going to be 2 negative, 2 negative, 2 negative, 2 negative, 2 negative. And then we've got vanadium. We've got 2 of them. And then the question is, what charge must each of them have to balance out the charges on all the oxygens? Plus 5, right? So in this case, because we've got 2 of them, each of them must be plus 5. Okay, so vanadium 5 plus. I'm going to erase this. And then over here, same sort of question. What must the vanadium be now? Plus 3. Because each oxygen's -2, that means all the oxygens are -6. So to balance out that -6, each of the vanadiums must be +3. Okay, so vanadium, did it gain or lose electrons? It must have gained too. It's becoming less positive, getting closer to neutral. So each V gained 2 electrons. So is this reduction or oxidation? Reduction. So vanadium was reduced. Okay, and then up here, this looks pretty dang similar to our last problem. Hydrogen in this case was neutral. And then over here, we said hydrogen behaves somewhat ionic because it's attached to an electronegative atom. That means we treat this as H+, and I'll put that in quotes. All right, so in this case, each hydrogen lost 1 electron. That means hydrogen was oxidized. So again, if we count the number of electrons being transferred, we said vanadium gained 2. However, we had 2 vanadiums, so that's a net transfer of 4 electrons for all the vanadiums, right? And then if we look at hydrogen, we've got 4 hydrogens, each of which gained 1 electron. Lost 1 electron, so that's a net transfer of 4. So we've got 4 electrons moving in both directions.
I don't get the whole, how hydrogen is,
So hydrogen up here went from neutral because it was by itself to being H+, +1. So in order to go from neutral to positive, it must have lost a negative charge. So it lost that 1 electron. Does that make sense?
Yeah.
Let's go back to the chart, right? So we said hydrogen in this case was neutral at first, and then it became more positive. It was H+. So because we're going in the upward direction, it's oxidized, right? So anytime you lose electrons, you're losing a negative charge. That means what's left over must be more positive. It's a little weird to think about it that way. Okay, so let's go back, take a look at this. What's our oxidizing agent? So our oxidizing agent must have been the thing that was reduced, right? So in this case, our oxidizing agent must have been that V2O5. And then if we look at the reducing agent, our reducing agent must have been what? Yeah, the hydrogens, the hydrogen gas, because that was the thing that was being oxidized. And then conversely, we said if we want to identify what was oxidized versus reduced, we look at individual elements. And we said up above that hydrogen, the element, was oxidized, and vanadium, the element, was reduced, right? So we do have to keep track of all of those. All right, what we'll do is continue this on Monday and do more practice problems. But what I would recommend is try reading through your textbook. This chapter is notoriously tricky because there's terminology that's very confusing. So try to read through your textbook. If you need to schedule an appointment with me or stop by an SI session, I would encourage you to do that as well.